Hello everyone, welcome to my presentation. I'm Kaisong Huang. Today I want to talk about Skeena, an approach to efficient and consistent cross-engine transactions. This is a joint work with Jianqiu Zhang, my advisor Tianzheng Wang from Fraser University, and our collaborator King Liu from Huawei Cloud Database Innovation Lab. Traditional database engines are storage-centric. They assume data is storage resident and optimize for storage accesses. However, modern database servers normally feature multi-core processors and a lot of DRAM that fits the entire working set or entire databases, which enables the emergence of memory-optimized database engines, including the good commercial ones like SAP HANA, Microsoft Hackathon, which can deliver very, very high throughput. Now, suppose you're a database management system architect, and you say, let's use a main memory database engine, it's very fast. However, someone might say DRAM is very expensive. It's hard to change the entire application, and we might have to deal with a lot of compatibility issues. For example, the interfaces could be very different than the old ones. This is exactly when a multi-engine DBMS comes to the rescue. So what is a multi-engine DBMS? Basically, multiple database engines are managed by one system. Normally, you have a fast engine, which is memory optimized, and a slow one, which is storage centric. Then you come up with a table placement scheme that suits your workload. For example, you can have orders table in the fast engine and the products table in the slow one. These engines implement their own transaction management. For example, when you execute a SQL statement that joins two tables which have been stored in different engines, it first goes through this common SQL layer where you have parser, optimizer, networking handler, etc. And then the SQL layer dispatches sub-transactions to the corresponding engines. By sub-transactions, we're talking about transaction abstractions that are already implemented by each engine. It sounds trivial, doesn't it? At the end of the day, aren't we just starting and committing engine-level sub-transactions? Well, the truth is, in the real world, we still need to deal with a lot of challenges. For example, inconsistent snapshots. Snapshot isolation is widely supported by database engines nowadays. Briefly speaking, each transaction gets a snapshot of the database upon start and sticks with it until commit. When we only have one engine, the idea is very simple. For example, here, we can have transaction S and transaction T working on their own snapshot without conflicting with each other. But things could get a bit messy when we have multiple engines. A transaction needs to see one big consistent snapshot of the whole system that under the hood consists of snapshots from all the participating engines. And the transaction always starts from one engine to another, which means it obtains snapshots one at a time. For example, when we have two engines, transaction S starts at 2000 in engine 1. After a while, transaction T starts at 30 in engine 2. After some transactions commit and bump the timestamp of engine 2, transaction S touches it and obtains its latest snapshot. Same thing could happen to transaction T. Now it turns out that T sees the fresher snapshot of engine 1 than S does, and S sees the fresher snapshot of engine 2 than T does, which means S and T start before each other, which is never supposed to happen. The key issue here is how to ensure a global snapshot ordering. Of course, there are more challenges to be dealt with. We can have serializability issues because even if both engines guarantee full serializability, the overall execution may not be serializable. We can have atomicity and durability issues. Therefore, commit checks are needed in addition to a traditional 2PC protocol. Based on these facts, we want a solution that incurs low overhead to retain the performance of the faster side. We want something that can keep engine autonomy as much as possible, something that supports full functionality, for example, various isolation levels, and we want something that can be easily adopted. Now with Skeena, we can keep all the desirable properties. We named our solution after the river Skeena, that is a major transportation artery in the beautiful British Columbia where my lab is based. Likewise, our Skeena is a key component in a DBMS that supports cross-engine transactions. Then what exactly is Skeena? It consists of a cross-engine snapshot registry, CSR, that tracks and selects snapshot, and a commit protocol for multi-engine database systems. It is a cheap way to enforce global ordering by leveraging the characteristics of fast, slow multi-engine database systems. More specifically, the global ordering follows the memory-optimized engines ordering because it is cheaper to get snapshots in memory-optimized engines than in storage-centric engines. Cross-engine snapshot registry is the table that maintains the mappings of snapshots between different engines. Now let's take a look at how Skeena avoids inconsistent snapshots by using CSR. First, let's revisit this example of inconsistent snapshot when CSR is not in place. Basically, transaction T sees a fresher snapshot of engine 1. On the other side, transaction S sees a fresher snapshot of engine 2. Which means S and T start before each other, and we all know this should never happen. Now let's start over and see what will happen when CSR is in place. This time, when transaction S want to access engine 2, it will first check the CSR table and know that there is some transaction T that starts later than itself in engine 1 with the timestamp 100 in engine 2 already. To keep the global ordering consistent, transaction S get a snapshot that's no fresher than T in either engine. Therefore, it will select the snapshot at 100 in engine 2. The mechanism of CSR seems very simple, it works very well, but since it's a central coordinator, are we introducing a new source of bottleneck? Actually, no. Querying CSR is very lightweight. Before we dig into Skeena's approach, I want to talk about other approaches that we have also thought about. The most naive way is to do a full table scan, which obviously can incur a lot of overhead because this table could easily grow by a lot. Therefore, we wanted to build indexes for each engine's timestamp. However, it's just too complex to maintain consistency across different indexes and deal with concurrency issues. So what Skeena does is pick an anchor engine, which typically is the fast one, and all the transactions follow the snapshot order in the anchor engine because it is cheap to acquire snapshots in the memory optimized engines. The CSR table we just saw essentially is just a range index that uses the anchor engine snapshots as keys and the lists of snapshots in the other engine as values. Maintaining one big index is bad for performance and garbage collection. Therefore, we need to create multiple of these indexes. The capacity of each index is fixed but configurable. We add a new index only when the previous one is full, and the recycled inactive index is by the predefined threshold. The other important component of Skeena is the atomic commit protocol. Because we want our cross-engine transactions to commit either all or none of its sub-transactions. Firstly, sub-transactions pre-commit and obtain their commit order from each engine. Then CSR does the commit check to see whether the transactions can commit without violating correctness criteria, for example, snapshot consistency. Next, sub-transactions post-commit to mark new records as visible, finalize log records, etc., etc. In the end, post-committed transactions go through the commit pipeline to have log records persisted and notify the client. Please check out more details in the paper. We explore the effort needed to adopt Skeena in a real-world system by integrating a memory-optimized engine ERMIA into MySQL and making it work with the default storage-centric engine InnoDB. This only required no code changes in ERMIA and less than 100 lines of code in InnoDB. Skeena itself is built upon 555 lines of code. We did our experiments on a machine with 40-core dual-socket Xeon processors. The MySQL client and server run on different sockets. We did thorough evaluation on single-engine and cross-engine performance with YCSB-like micro benchmarks and TPCC. Single-engine performance is not affected by Skeena. ERMIA-S here is ERMIA with Skeena enabled. Similarly, InnoDB-S is InnoDB with Skeena enabled. As we can see, with Skeena enabled, the engines still retain their original performance. For more experience and more insights, please check out our paper. Now I want to share some hands-on experience on how to use Skeena based on TPCC results. Apparently, we want to put more tables in the memory optimized engine for performance, or put more tables in the storage-centric engine for low cost. This is a heat map of throughput of different transactions in TPCC. From bottom to top, we start from having all the tables in InnoDB and gradually move tables to ERMIA. As you can see, all the transactions get a speed up but have different sweet points. Here, I want to recommend 3 table placement strategies based on these results. The first one is payment opt, where we only place customer tables in ERMIA to make payment and order status transactions happy. The second one is new order opt, where we place customer and item tables in ERMIA to optimize new order. And the most aggressive one is archive, which places all the tables in ERMIA except history tables in InnoDB for relatively lower storage cost. In conclusion, cross-engine transactions are useful but were poorly supported before Skeena because of correctness issues and functionality limitations. Skeena is an approach to efficient and consistent cross-engine transactions that uses CSR to manage snapshots and pipeline commit for atomicity. It is easy to adopt it in the real-world systems. It incurs negligible overheads and maintains the benefits of memory-optimized engines. If you like our work, please find out more in our paper and code repository. Thank you.